This is a video explaining how we do bonding in compounds that contain two nonmetals connected together. The electrons are shared unlike they are in ionic compounds. And so the starting point for a Lewis structure is the Lewis dot symbol for an atom. So let's do an example of carbon, which has 4 valence electrons because it's in group 4A or group 14, depending on which periodic table you're using. And we'd like to put 1 dot on each side for the following reason. All right, so from the electron configurations, we saw that having a filled S and P shell gave you a noble gas electron configuration. Well, that's 8 electrons, and it turns out that in the nonmetals, they all want to have 8 electrons around them. Well, carbon only has 4, so how can it get 4 more? Well, it can share electrons from 4 hydrogens, for example. So in comes a hydrogen atom, and I'm going to do it in a different color so that you can see the origin of where the electrons are coming from. And we bring in 1 hydrogen for each 1 electron. Okay, and so this electron in carbon is being shared with this hydrogen, but this hydrogen's electron is being shared with carbon, and that way they both get to count the electron. So hydrogen thinks it has 2 electrons, just like helium, the noble gas, and that's true for all the hydrogens, and carbon thinks it has 8 electrons. So drawing a structure with 8 electrons around all the nonmetal atoms, besides hydrogen, which needs 2, is called the octet rule. Okay, and so Lewis structures are sometimes called Lewis dot structures. Now another way of actually writing this is with dashes. And whenever you see a dash, think 2 dots, 2 electrons. So this would be perfectly acceptable as a Lewis structure, because everybody understands that the bond is 2 shared electrons. All right, so that's one example. And so when you do a few of these, you see that what more or less happens is that in most of the cases, you can draw a Lewis structure by saying, okay, you have an atom, it has so many electrons, it needs so many more, and that's how many electrons it's going to share with somebody else. Because usually what happens is it shares 1 electron and gets 1 shared back. It counts them as 2. All right, so let's do another element, and we'll go next in the periodic table to nitrogen. Now nitrogen has 5 valence electrons because it's in group 5A. And let's bond it to hydrogen as well. Whoops. See, we have a pair of electrons here, so we don't need the hydrogen on that side. So nitrogen has shared 3 electrons and has 2 that are not shared. And so this is called a lone pair. And so we can draw the shared electrons as dashed just like before, and so the Lewis structure for ammonia can be drawn this way. Now, if you're expert enough, you would recognize that the structure as I've drawn it so far does not have 8 electrons, but everybody knows that nitrogen has a lone pair. Okay, so it's quite possible that you will see Lewis structures without the lone pairs being shown on atoms like nitrogen or oxygen or some of the halogens. Okay, so as you go across the periodic table, anything in group 5 is going to have 1 lone pair. Anything in group 6 is going to have 2 lone pairs. Anything in group 7 is going to have 3 lone pairs. All right, so let's go to group 6, which is oxygen. And oxygen has 6 electrons, so it's going to have 2 lone pairs because it doesn't need to share but 2 electrons. Let's go ahead and share 2 electrons and get 2 electrons. Now oxygen has 8, hydrogen has 2. This is water. This is ammonia. This is called methane. These are very common materials, and you should know the names of them. All right, and so the Lewis structure for water, H2O. Okay, notice the one thing about H2O, the hydrogens are on the outside. hydrogen's on the outside, hydrogen's on the outside, because hydrogen's never in the middle of anything, because that would be 2 bonds and at least 4 electrons, which hydrogen really does never do. All right, so this is the Lewis structure for water, and there it is with the lone pairs explicitly shown. Just to recall that I told you that oxygen in a Lewis structure may not have the lone pairs shown to you if you go looking on the internet or in other textbooks or other things like that. But you're expected to put on the lone pairs because I want to see explicitly 8 electrons. All right, let's do a few more examples. A little more complicated. Let's look at PCl3. All right, so the first thing to recognize is, all right, now who's on the middle, who's on the outside, who's connected to who? Because that's really the first question you have to figure out. Well, so when you see a formula like this, you think, okay, I've got the first one, it's usually in the middle. The second one's usually on the outside. And so let's go ahead and do that. We'll draw, and we know that it's going to be at least 1 bond to each. All right. Now, the other thing is thinking probably if phosphorus is sharing 3 electrons in these 3 bonds, it's got 2 more. It doesn't need to share any. So it's going to probably have a lone pair and then 3 like this. Now, chlorine only needs to share 1 electron because it already has 7. So the dot structure for chlorine atom, let me just remind you, 1, 2, 3, 4, 5, 6, 7, only needs to get 1 more electron. So it will share 1 to get 1. So halogens usually have a single bond to them. But 3 lone pairs. And you get pretty quick at drawing these dots. And that's the Lewis structure for phosphorus trichloride. All right. Now sometimes you have to not obey the octet rule. So there's a few exceptions. One is if you're in group 3, you only have 3 valence electrons. Generally, you only draw a structure with 3 bonds to it because it only has 3 electrons to share. So BH3 would be boron, hydrogen, 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 and that's it. You have no more than 6 electrons. You can't obey the octet rule with 6 electrons total. Sometimes you have too many electrons. All right, so if you go below group row 2 in the periodic table to period 3 and so on, to elements like phosphorus and sulfur, you can have more than 8 electrons. That is to say, you can have more than 4 bonds to them. So let's look at phosphorus pentachloride. This is a compound that does form. And so now phosphorus pentachloride is what happens when you take phosphorus and you say, okay, well normally you would like to have 3 bonds in a lone pair, but now we're going to have to use all 5 electrons because we have 5 chlorine atoms bonded to phosphorus. All right, so instead of having a lone pair, it's going to have 5 bonds. Of course, squeezing them in somewhere could be difficult. So that's the Lewis structure for phosphorus pentachloride, and you can see it automatically violates. It has 10 electrons around phosphorus, but that's okay. Phosphorus will do that. And so the main reason I bring this one up is because you might see 2 common exceptions for phosphorus and for phosphorus and sulfur, and that is when you go to phosphate, which is PO3 3 minus, sorry, PO4 3 minus. Okay, so first of all, the Lewis structure of an ion, we draw in square brackets and we put the total charge of the ion on the outside. So this is the Lewis structure for phosphate, not showing lone pairs on oxygen. You add all the electrons on oxygen. So notice that this oxygen has 3 lone pairs. That's very unusual, but that's it does happen. And so, of course, whenever you draw a Lewis structure, it's always a great idea to count the number of electrons because you should never draw more or less electrons than you actually have. So go to the periodic table and you say, okay, phosphorus has 5 valence electrons, oxygen has 6, there's 4 oxygens, and so it's 6 times 4 is 24, 24 plus the 5, 29, plus 3 more electrons, 32 electrons. And so then you look and see, are there 32 electrons here? If they're not, then you've got to take some away if you have 34, or if you have 30, you've got to put 2 more in. So one way is you can count by 8s if you know what you're doing. So there's 8 around that oxygen, 8 around that one, 8 around that one, 8 around that one. That's 32 electrons. Real quick to count to 32 by 8s. All right, and so that's what you might see for phosphate. Now you could draw a Lewis structure where they're all single bonds and 3 electrons on the oxygen. So there are some textbooks that actually draw it this way. The other is sulfate, which I'm going to squeeze in up here. You could draw one with all single bonds, but it's also very common to see sulfate, which is SO4 with 2 extra electrons, 2 minus, and 1, 2, 3, 4, 5, 6, 1, whoops. And when we look at sulfate, it has also, when you count the valence electrons, 32, and so 8, 8, 8, 8 makes 32. So this is a Lewis structure for sulfate. Okay, so this happens in the row 3 and below. This cannot happen for nitrogen. Nitrogen can't do this. Oxygen can't do this either. So this is only for row 3 and below that you violate the octet rule by having more than 8 electrons. All right, well that's that.